Uh, Hello, I'm YKY. I'm from Hong Kong, and I'm not wearing clothes, so I use this filter. But you can reverse it, but I suggest you not to do so. But if you want to discuss AGI, you are welcome to contact me. First, I will talk about BERT or GPT. BERT is the state-of-the-art language model that can do a lot of amazing things. And after seeing a demo of BERT, I am quite convinced that AGI can be built very soon. So I will explain why. First, we look at the internal structure of BERT, and the transformer is the key component of BERT, and it has a special property of equivariance. What this means is, for example, if the input is of this order, and if we change the order to say 231, then the output would also change in the same way, and that's the meaning of equivariance. Now, the inside BERT, the transformer is a series of these equivariant transformations acting on the input tokens, and during training, for each token, BERT is forced to predict the next token in sequence, and so it happens for all these tokens, but some of them may also be missing. And by this kind of training, the result is that we would have a high-level representation of the input sentence, which is much richer in semantics and contextual information. And we can make use of these representations to perform tasks such as question answering or logic inference. And I would also note that the input of BERT is linguistic, and its structure is similar to logic because they are both symbolic and linear. And the same could be said of the output. So we have a logic in, logic out transformation, and we can guess that what's happening inside these transformers is must be some kind of syntactic manipulations of the symbols, and this is similar to the logic engine, inference engine in classical AI. So I propose that the classical AI can be the BERT can replace the updating function of a classical AI engine with some necessary modifications. So in classical AI, we have some logic rules, and these rules perform the update of the working memory. By working memory, I mean like this part of the input, and it consists of a number of sentences, or and we could also regard them as propositions, and that this is the what I call the working memory. So I propose is that BERT can play the role of this update function, and with the advantage that it's much faster and can learn from a huge amount of data. In classical AI, the only problem is that we lacked such a efficient learning algorithm. And this is a more detailed view of the working memory, and it's in the form of a sequence of sequences, because we have multiple propositions, and each proposition may be decomposed into the atomic concepts. For example, this may be I love you, and you love me, right? And then the conclusion would be I would be happy. So that's what I mean by sequence of sequences. And this could be the basis of a AGI architecture. And we can do something like this architecture in reverse. So in here we have the logical knowledge base, and now we are trying to we have BERT, and we try to get back the logical data by extracting from the working memory. And then this long-term memory can later it can suggest propositions that help the inference by BERT. So what I'm saying is that if we think in terms of logic, then we can design these cognitive architectures more easily, because we know what's going on in these modules. So now I will talk a bit about the word embeddings. And inside BERT there is this positional encoding, which is in the form of sine wave, like these ones. And that there's also the word embedding. For example, the concept of love is represented by these activations. Notice that in this axis is not just one dimension, but many number of dimensions. And the word embedding is means the activation of some of the dimensions. And when the dimension is high, then the behavior of learning algorithm is dominated by the number of dimensions. So we see that the word, the concept embedding of love is still recognizable in even when it's partially erased by the positional embedding. And this is a special feature of the high-dimensional embeddings. And from this we can guess that these embeddings may be added together to composite meanings. For example, I plus love plus you would become a single proposition, like a predicate. So this would be a single vector. And it may be a feature used inside the representation of BERT. And by analyzing BERT's structure, I hope to shed light on how to design AGI better. Next we will talk about reinforcement learning. This is the lamprey, a relatively primitive organism. Its behaviors are very limited, with only eating, mating, and escaping from predators. So that makes it easy to study its brain mechanisms. From an evolutionary perspective, the lamprey brain consists mostly of what we now call the basal ganglia in higher animals. It has a relatively small neocortex as opposed to the primate, which is much larger in proportion to the basal ganglia. But interestingly, the neocortex emerged later in evolution, but its mechanism of making decisions is very similar to the basal ganglia. But its decision also overrides that of the basal ganglia. My understanding is based on these books. And first we look at the basal ganglia. Basically, it maintains a number of populations of neurons, and there are two here, and they compete for activation with lateral inhibition between them. And so eventually one population will win, and that will determine a single course of action for the animal. This is very significant for the animal's behavior. And this part of the brain is also highly concentrated in the dopamine receptors. And we all know that dopamine represents the temporal difference of reward in reinforcement learning. So the basal ganglia learns by reinforcement learning, and its function is focused on relatively primitive actions such as motion. So if in the Parkinson disease we know that dopaminergic neurons are impaired, and therefore the patients have difficulty in movements, but they are relatively unaffected in their higher cognition. So now we look at the neocortex, and it's segregated into multiple major networks, but the mechanism of decision making is surprisingly very similar to the basal ganglia. So there are some units or columns that are activated in the neocortex. But in here, the special thing is that they have excitatory lateral connections. So they are excitatory, and as a consequence of that, the populations can be activated for a much longer time, and that allows for longer deliberation of the options in the neocortex. And that's why higher animals have a much more complex register of behaviors. So I want to explore this idea that in the neocortex they may use a much more efficient learning algorithm than traditional reinforcement learning. In traditional reinforcement learning, the reward is a single number, and it doesn't distinguish between different types of rewards. But there is a hypothesis or theory that in the neocortex, different actions are associated with different kinds of rewards, and they are learned by association. And this algorithm is supposed to be faster or much more efficient than reinforcement learning. But we may regard that this may be an approximation of the Q-learning or the Bellman equation. So this is one idea that I want to explore and maybe may help the development of AGI. In the last part, I will talk about model-based reasoning as opposed to syntax-based, which I'm much more familiar. So if we use a bunch of logic propositions to describe the real world, then we have a syntactic representation. Whereas if we use for example, a set and points inside to represent the world, then this representation is semantic. And model theory is the bridge that relates these two areas. And there is a functor relating these two sides. So we look at one model-based method proposed by Pascal Hitzler. And so first we have a model of the world which is in the form of the interpretation I. And this I maps a bunch of atomic propositions to true or false. And so if we know that some propositions are true, then it forms a model of the world. And then there is this semantic operator, TP. P stands for a program. So TP maps the interpretation to the next one, the update of the interpretation. So this proposition used to be false, but now it becomes true. And this represents one step of logic inference. And further, his idea is to map this space of all possible atoms to the Cantor set, which is a fractal structure inside the unit interval. And so to map the interpretations to this K is the real numbers, and they use a level mapping called iota, and it has this form. B is a base number integer, and raised to the power of the level of the atoms, and then sum together. So for each interpretation, they get a real number, and so all the models can be mapped to a real number. And then they use a neural network to approximate this a semantic operator. So and it can be proven that the neural network can successfully approximate this map by using the continuity condition in the topology of the Cantor set. So I'm trying to consider this as an alternative to syntax-based reasoning. So, for example, we can have some regions representing sets, and then there are elements inside these sets. And when we change the shapes of these regions, then they will lead to different kinds of, different propositions being true or false. For example, if this point is outside or inside a region. The region, for example, if fx is bigger than 0, then this represents a region in high-dimensional space, and f can be a neural network. So this can be implemented as a neural network, these regions. But this scheme doesn't seem to be particularly efficient, because the shapes will change very slowly during learning. So I'm just trying to look at more possibilities, but this may not be a highly effective algorithm for AGI. And lastly, I also note that in my paper it's explained that the predicates have this vibration structure, which is very important for understanding the categorical treatment of predicate logic in a book that I cited in the paper. So this diagram is very important for understanding the predicate structure. And I also note that it has some resemblance with this model, but this is syntax based in the lower part. But this part of the presentation is kind of disorganized because I don't have enough Neocortex to figure it out, at least not now. So I will close with this, and thank you, and I'll leave more time for discussions.